Hello, Mile High Video 2020. My name is Kieran Kunhya, and I will be presenting native processing of transport streams to and from uncompressed IP. I thought I'd give you a quick introduction on who we are at Open Broadcast Systems. I'm sorry if you've watched my other presentation at Mile High Video, but this is the same slide. Basically, we're a company specializing in software-based encoders for sport, news, and channel contribution. This is generally business to business. We're based in central London. You can't see this, but to my left is Big Ben. Notably, we build everything in-house, and this includes hardware, firmware, and software. And most importantly, we're not to be confused with the other OBS. That's completely different. So let's look at some of the challenges in this field. One of the real big challenges in live production in live broadcast is it's still almost always based around SDI, which stands for Serial Digital Interface. This is coaxial cable based, as you can see. It's unidirectional and carries video, uncompressed video in the order of gigabits. It's very, very low latency of the order of video lines. This is microseconds, but it has a ton of problems. It's only lets you have a single video in one direction down a cable. And they use things known as SDI crosspoint routers to get signals around a building, for example. These have an inherent design structure of 1152 signals by 1152. And we'll discuss later why that's a problem. Coaxial cable has cable length limitations, in particular for very high bitrate signals such as 12 gigabit UHD. This really does affect your cable length in large facilities. And these SDI routers are getting full. There's so much content out there that viewers want. There's something known as quad link that's used for UHD. So this is essentially running 4 of these SDI cables in parallel. And so many other reasons why in many facilities SDI routers are full. And so as I mentioned, huge amounts of video content for ultra high definition, over the top services, remote production. Probably don't have time to really explain that, but that's covered in the other presentation I'm giving. These are often coming in externally, be it sports, news, etc., as MPEG transport streams. And they often also need to be delivered to other facilities or to end users as MPEG transport streams, but in the middle be uncompressed. And so the broadcast industry is looking to other industries such as cloud, big data, etc., where network rates are much larger. So the switch shown has dozens of 100 gigabit ports, which are bidirectional, and tens of terabits of overall switching. This is much, much more scalable than traditional SDI, and it's future-proof. So it's capable of doing 8K, it's capable of doing VR, it's capable of doing object-based video, and whatever someone else decides to invent in the future. And this is comparable to SDI routers with tens of thousands of flows at any given time, sometimes more. Traditional broadcast workflows are relatively static. They require lots of manual patching of SDI cables. Someone has to go in, plug cables in to make relatively simple changes. And kind of as a result, it means that equipment in this area is heavily biased towards static, fixed function. You buy a box, it will always do one thing in its entire life. It may do that thing very well, but it will still only be doing one thing. And really, it would be nice to use IT equipment that could be scaled up and scaled down in a fashion very common in the cloud, but without having to repatch things. And so one of the big problems with many facilities that decide to move from SDI to uncompressed IP is they basically reinvent the past. It's historical reenactment. And the way I like to explain it is like saying, don't invent the internet to use it to send more faxes. Actually, make the most of what you've got. For those of you who don't know what a fax is, I suspect that's becoming some of you. Please Google it. So quite a bit of what I'll talk about will be based off one of the projects we did, based around Sky UK's master control room. I'm sure as a organizer of this event, they won't be too upset about that. But it's a very interesting project and had very, very complex engineering challenges. So where did it all begin? For us, it began in 2015 when Sky News UK and Sport decided to merge their MCR, and there was a possibility about 5 years ago for upgrading to 2022-6, and I'll kind of explain what that is later. And really, they have hundreds of encoders, not just ours, and decoders for contribution, getting content to and from all over the world. And in the end, this was run as SDI for 1.5 years, and became a lift and shift, so literally taking equipment down the road. And one of the reasons they had to do this was because their SDI router was full. This was quite challenging, this process, because it required an overnight upgrade where operators needed to migrate equipment themselves. And as you can see from the picture, there's huge amounts of content. It's worth sort of making a COVID comment. This is 2020. Cannot really go without making a COVID comment. There are often needs to immediately scale up encode capacity in particular to get content to people's homes in a point-and-click fashion. This would be completely unthinkable in SDI land. It requires someone to go in, plug in cables, set up routing, etc. And this could just be done as a point-and-click process, which is completely unthinkable and remarkable in many ways. So let's step forward to 2019, 2020, where we worked with a well-known consumer brand doing sports. They had a project that was about 2.5 months from commission to deploy, which is a bit scary. And in the end, this required a world feed of a particular sport to be decoded to 2110 in a physical facility for downstream processing. Pretty common 15, 20 megabits, H.264, 4 to 8 pairs of audio. It's pretty substantial. Interestingly, the content could be 1080i 25 or 2997, and in the end, they chose a 16-channel single flow at 125 microseconds. So that means every 125 microseconds there had to be an audio packet on the wire, and there could be up to 15 concurrent matches. And what we ended up doing was choosing this device here. It's a kind of blade-style server. But what was remarkable is 2 full racks of traditional 1U SDI encoders or decoders can be replaced in 2U. And in this example, we're using 25 gigabit interfaces. And they could be CPUs or RAM could just be added as needed to scale up. And we really envisaged the broadcast facility of the future to look exactly like this, just racks and racks of this, entirely like a cloud facility. And what was notable is this could encode 64 channels, sometimes even more depending on the configuration, in 2U. Again, replacing 2 full racks. It's worth going into some of these standards from a software engineering standpoint. So there are plenty of presentations online, very bureaucratic, going into all the bureaucratic detail about different standards, but there's very little information about how to do this from a software engineering standpoint. Unfortunately, I don't really have time to go into the real subtleties, but put simply, 2022-6, that maps SDI data directly. So the SDI data is the data including raw blanking, as you can see on the picture on the right, directly maps this bit for bit exactly. And then there's something known as 2110. This has separated flows. So audio, video, and ancillary data go on a different flow, and it has some of the legacy blanking removed. The most challenging part from a software implementation is they both have very tight timing. Packets need to arrive within microseconds because there's hardware out there with very, very tiny buffers, if any buffers at all. And so these problems are very challenging engineering problems and really multidisciplinary. You've got to understand broadcast, you've got to understand high performance networking, and you've really got to understand multimedia. Very high data rates of UDP traffic. One doesn't simply receive 1 million packets a second. Again, and many gigabits of video. Really unusual pixel formats. I'll talk about that more later. Software works in an 8 to 16 bit, but there's things like PAC 10 bit in 2022-6 and 2110. Again, very, very tight timing requirements for software. And for us, this has been about 5 years of work. I've spent basically all my working life on this. So this is a massive problem. So one of the things that we do to handle these high bit rates is use something known as kernel bypass. And essentially what it does is it memory maps network card memory straight into user space. So you don't have to talk to the OS to get these packets to and from the wire. Plenty of libraries out there. DPDK is probably the most famous one. There's netmap, which we ended up using. There's registered I/O, and in particular, it avoids costly memory copies. And put simply, what we're doing is effectively rendering uncompressed video to and from the network card. Just like a video player renders video straight to your GPU for display on the screen, we are rendering it to the network card for delivery on the wire. There are lots of pixel formats that you have to deal with. In YUV422, for example, you could have plain 10-bit. If you have a 10-bit video stream, that's your common working format. You could have 8-bit if a feed that just happens to be coming in 8-bit. The SDI data stream uses UIVY 10-bit, but 16-bit aligned. Some broadcast hardware uses Apple's V210 format, slightly different. And you could also have contiguous 10-bit video using 2022-6 or the packing in 2110, also known as RFC 4175. You can see why I didn't go into all the acronyms. But the last two in particular are very tricky to work with in software. They're not common. And so what we do is use something known as single instruction, multiple decision instructions on the CPU. These are specialist instructions designed for vector operations. And what we do is we write these by hand. We don't use tricks such as intrinsics for every single pixel format mapping to every other pixel format mapping. And there are also some others for various reasons. And this has a phenomenal speed improvement, 5 to 20 times. That's not a percentage sign compared to, say, doing it in C. And we do it once, then make it fast once and for all. Well, at least until a new CPU comes along, such as the Apple M1. I would point out that a generic pixel conversion library is one of the most difficult problems in multimedia. If there was a Nobel Prize for multimedia, someone who could solve this would get this Nobel Prize. The way to do it is if you want to go from pixel format A to C, you go via an intermediary B. But this intermediate pixel format is always a compromise. And so what you do is you add special cases, but then you keep adding special cases until you've done them all. So these pixel format conversions are a really, really CPU intensive part of the operation. And so they're a massive, massive problem. And so what we do is combine these two techniques. We combine SIMD and kernel bypass, and this achieves a massive, massive performance improvement. Essentially, we're doing pixel transformations, high performance pixel transformations, straight into network card memory. And this gives us a massive, massive speed improvement. I can't emphasize this more, 100 to 200 times. That's not a percentage sign speed improvement. I mean, the size of this improvement just cannot be understated. It's the end goal of years of work. Timing, unfortunately, I'm not going to be able to really go into the subtleties of precision time in 2110, but the key question from a software engineer standpoint is how on earth do you send a packet precisely within 20 microseconds or some number like that? You've got three things to deal with. Frequency, so you've got to send video frames exactly at the correct clock frequency. You've got to handle phase, so you've got to get the first packet of the video frame transmitted exactly at the right time. And packet burst, so this isn't analog, so you can't just burst packets on the wire. And these are three coupled variables. You have to make sure all three don't deviate, because if you change one, the others move as well. This is a bit like a missile. The missile knows where it is at all times. It knows this because it knows where it isn't. By subtracting where it is or where it isn't from where it is, whichever is greater, it obtains a difference or deviation. That's the crux of how a missile works. You've got to mind the gap. 2110 requires a clean gap, no packets at all where there was vertical blanking. So in the previous picture, there was something called the vertical blanking. That's some historical artifact where the electron gun went back to the top of the screen. It's not at all easy just to create a clean walled gap in software. So in practice, you've got to stuff it with other data. That's a very difficult problem. Uncompressed audio is a real problem as well. As I kind of mentioned before, we're using 125 microsecond packets. These are really small, and at 48 kilohertz, there's 8,000 of them every second. And we'd really rather not use kernel bypass for these low bit rates. It's only 30 megabits. But at 8,000 packets a second, that's a huge number of system calls. And it's very costly. The way to measure this is to use something called a flame graph. This is something created by a Netflix engineer. And it shows how function calls take time. And it helps you understand how to tackle slow functions. But there's a problem. This flame graph doesn't really have anywhere to cut. The flames are long and thin. You'd love to have, a function that's taking up a ton of time, so you could speed it up by a factor of 2 or 3, and that would save you a ton of problems. But you can't here. It's death by 1,000 cuts. So some general software comments. It's really challenging to maintain a modular code base with uncompressed IP. There's tons of technical debt that accumulates We've had to do 3 or 4 large rewrites that have taken months on end each. It's very hard to use standard programming paradigms such as reference counting, especially when you've got things like 125 microsecond buffers. You're reference incrementing them, decrementing them thousands and thousands of times a second. You have hundreds of thousands of ref count changes. It involves very tight integration with an application. I compare this to an electric car and a gasoline car. You can't just take the engine out of a gasoline car, put it in an electric engine, and expect it to behave the same thing. It's a massive design change. You can't just use whatever fashionable language of the month there is. I'm not fashionable, so I wouldn't know. But you can't use things that have garbage collection. You can't just sleep for a couple of milliseconds. That's just too much. Interoperability was a massive pain point. In particular, one decapsulator expected the source port to match its destination port. That took a long time to figure out. Many of these devices don't do what a simple cell phone can do and verify IP checksums. Not all of them can handle 16-channel flows. Some analyzers and receivers just expect perfect time data. Otherwise, they just crash within minutes, sometimes days. One of the biggest problems is that most receivers clearly are using packet arrival times and not the timestamps. You can set the timestamps to 0 and most equipment will work fine. I've seen facilities where timestamps go forward, backwards, left, right, and center. And that's a big problem for a native IP encoder such as ours, which is going to use the timestamps to synchronize the audio. It's got no other way. So how can we conclude? Well, there are large operational improvements by using uncompressed IP video technology, but this is not the same as, say, web video. This is not FMPEG.C, and you'd be trying to compare a road car versus a highly precisely tuned Formula One car. It's completely different. It's taken us years of work to really understand how to do this stuff. This is all bare metal. We'd really like to containerize it next in the future. That allows even more flexibility. Dynamic addition of processing functions in the live broadcast environment would be really cool. So thanks for listening, and I believe it is now question time.